Okay, so to wrap up the things that are covered in Chapter 7, one thing that we want to understand is what a fuel is. So we've been talking a lot about enthalpy changes for chemical reactions, and a very practical importance of that is when we use fuels, which are things that we obviously use in our everyday life. So the formal definition of a fuel is just a substance that has a lot of stored energy. So the more energy that's stored, the better the fuel that it potentially could be. And the whole idea is when we use a fuel, we're going to release that stored energy and convert that stored energy into something else. And usually the way we release that energy is just by burning the fuel. All right, so all the traditional electric power plants and car engines and all those things, they're burning fuels to release the stored energy, and then they're converting that stored energy into something else. So what we mean by stored energy is that when you burn the fuel or expend the fuel, however you choose to do that, there's a lot of enthalpy that's released. So you have a very negative delta H, and all that energy is released to the surroundings, and you're able to use it to do something else. Now, the types of fuels that we use today, most of them fall into the category of fossil fuels. So these are ones that are formed by decomposing living organisms. So when something dies, it goes underground and then is slowly decomposed over many millions of years and generates what are called fossil fuels. And this is a very slow process, so the fuels that we use require millions of years to generate, and then we dig them out of the ground and use them for our everyday life. So most of the fuels that we use today are fossil fuels, things that you're very familiar with, like gasoline, coal. We'll talk more in detail about some of these. These are all considered fossil fuels. And a lot of natural gas that we obtain naturally through fracking and other processes, that's also considered a fossil fuel because it was generated through those similar types of pathways. So there's two major types of fossil fuels that we use today. There's petroleum and coal. Petroleum is a liquid and is mostly made up of hydrocarbons. All right, so hydrocarbons, we've seen that word a couple times already. It means something that has only carbon and hydrogen in it. So hydrocarbons have the general formula CXHY, so just carbon and hydrogen in some ratio is a hydrocarbon, and most of petroleum is made up of hydrocarbons. You have it's typically a liquid, or most of the products that we get from petroleum are liquids that we're going to use. And then what we do with petroleum is it's buried under the ground. We use as we're all familiar with in Houston, we use oil wells to bring it up, and it's a mixture of all kinds of different compounds. It's not just one thing. And so what we do is we separate the petroleum using physical and chemical processes into a bunch of different components that we use. So the ones that are the most lucrative for the oil companies are the transportation fuels. Gasoline, diesel, and jet fuel. And gasoline, diesel, and jet fuel, again, are mostly made up of hydrocarbons. The difference is the number of carbons that they have. So the gasoline is sort of on the shorter end, usually around 8 carbons or so. Diesel is a little bit higher, maybe 10 to 15, and then jet fuel has the highest number of carbons. So the only difference between gasoline, diesel, and jet fuel is just the number of carbons they have in their structure and the number of hydrogens. And when we get petroleum out of the ground, we separate it into those fractions and many others. So there are many other products that come from petroleum as well. Some of them are, not all of them are even used as fuels. A lot of, plastics that we make are petroleum-based too. So we get a lot of different things from petroleum, but it's a liquid source of fossil fuels that we can get from the ground. The other type that we often use is coal, which is it's a solid form if you've ever seen it, and it's mostly made up of carbon. So it'll have some hydrogen, oxygen, sulfur, some other things in it, but most of it is carbon, and it's a solid. Now, there's different types of coal, and depending on where you get it from or how long it's been, buried underground, it can have different amounts of carbon in it. So not all coal is exactly the same. And the key principle that we want you to know for this section, we're not going to ask you a lot of really in-depth questions. There might be some on the homework just to really get you some practice with it. But for exam questions, we're not going to ask you a lot of details about these things. But the thing we should realize about coal is that if you have a higher carbon percent, so the more carbon that you have in coal as a percentage of its total composition, that has more stored energy. All right, and the reason is we know that when we do a combustion reaction, we're taking something and converting it into carbon dioxide and water. If your carbon is already partially oxidized, if it already has some oxygen in it, there's less energy for it to release as it gets fully oxidized. But if you burn pure carbon, you have more stored energy because you have more chemical reactions taking place to get you to pure CO2. So if it has some oxygen in it, it's already partially burned, and so the more pure the carbon is, the less it is, the less it's already been oxidized and the more energy that it has to store. Okay, so the more desirable forms of coal are the ones that have the higher percentages of carbon. Now, we've been using fossil fuels for many years now, for many decades, and there are some concerns about them, as we're probably all familiar with if we follow the news. So one is the idea of greenhouse gases. So greenhouse gases are important and necessary for our survival on this planet. So the primary greenhouse gases are water, methane, and CO2, the ones that are currently in the atmosphere today. They trap heat. So when the sun heats up the earth and then that heat radiates off the surface of the earth, these greenhouse gases trap it, and they help keep the earth's surface warm. All right, so it's been long known that these gases have this effect, that they keep the surface of the earth warm. I think in the book it says the temperatures. The average surface temperature of the earth is somewhere on the order of 15 to 20 degrees Celsius over the whole world, and if it wasn't for these greenhouse gases, it would be something like minus 18 degrees Celsius, pretty much uninhabitable. So the greenhouse gases do help keep the planet livable, but then there's some concern about what would happen if we start pumping them into the atmosphere. So whenever you burn a fuel, especially CO2, a lot of that comes out as a product of those combustion reactions, and we're increasing the concentration of CO2, and there's concern that that's going to lead to unnatural warming. Now, regardless of what you read in the news, the problem of man-made global warming is a very complicated one, which I don't care to get into during your chemistry class. But these greenhouse gases may warm the planet unnaturally, and that could, cause problems later on. But there's still, ample debate about the effect of those, how big of an effect this is going to have, how problematic it's going to be, and whether we can't even do anything to stop it. So I'm not going to get into those side debates here, but that's one of the concerns about fossil fuels. And there's also another concern about fossil fuels, which is long-term viability. So as I told you at the beginning, it takes millions of years for these fuels to form. So, and there's only a limited amount of them in the earth right now. So these fossil fuels won't last forever. I've seen different estimates for when they'll run out, and we probably have, at least 100 or 200 years before we even have to start worrying. But at some point in the distant future, we're going to potentially run out of fossil fuels because it takes millions of years to replenish them. And when people first started burning these things, hundreds of years ago, didn't really think about this problem, but the fuel that they've taken out of the ground and burned up until today has not been regenerated yet because it takes millions of years. So at some point there's the possibility that we're going to run out of fossil fuels and we're going to have no choice but to go to alternative fuel sources. So then the last topic that we'll cover, which is also in Chapter 7 of your book, are what are some of the alternative energy sources. So, fossil fuels are great because they're cheap, and right now they're abundant, and we can use them in so many different ways. But what do we think about as we move into the future? And this sort of drives a lot of the research and development that's going on today. So there's many proposals for the future. A lot of them revolve. We've probably all heard of solar energy. That's a way of supplying energy to your home. But we need some way to store energy too. We still need fuels for the future. We can't imagine a world that doesn't require fuels. So the two fuel sources that are probably most heavily debated or talked about for the future are hydrogen and biofuels. So hydrogen is great. We've talked about many times how when hydrogen burns in oxygen, it releases a ton of energy. So it has a very high what's called gravimetric energy density, which is energy stored per weight. We know that the atomic mass of hydrogen is very small. It's only 2 grams per mole. And so if we take H2 and we burn it with O2 to make water, that's what happens when we burn H2. The delta H for this reaction is minus 286 kilojoules. So that's a lot of energy that's released for burning a little bit of hydrogen, because 1 mole of hydrogen has a mass of 2 grams. So with 2 grams of hydrogen, you get 286 kilojoules. There's no fuel in the world that has anywhere close to that high of an energy density. Now the problem with hydrogen is twofold. One is that right now it's expensive to produce. We don't have a good way to make hydrogen. There's not a huge natural source of hydrogen that we can tap into, so we have to produce it ourselves. And all of the currently available methods for producing hydrogen are expensive. A lot of them also require fossil fuels at the moment, so that's not very helpful. And then even the ways that we make hydrogen that don't require fossil fuel, that requires a lot of energy and a lot of expensive equipment to do that. And the other big difficulty with hydrogen is, as we know, it's a gas, so it's difficult to transport and store. So all the transportation fuels we use today are gasoline, jet fuel, all those are liquids, which makes it easy to put them in a tank and transport them. You can transport them through an underground pipe in many cases. Not so easy to do that with hydrogen, which is a highly combustible gas. So there's some physical challenges associated with hydrogen as well, even if we were able to make it a lot more inexpensively. Now the other proposal that's been tossed about in recent years are what are called biofuels, and there's a lot of different approaches that fall into this category. These are fuels that are generated from plant matter or produced by microorganisms. So this is basically using biology to make fuels for us. And there are some ways we can do this. And some of the primary products of this biofuels approach are, a lot of people are looking at alcohols now, so methanol, ethanol. So if anybody that fills up their gas tank today knows that most gas that you buy today is already 10% ethanol, and a lot of ethanol can be produced from biofuels in a renewable way. And then there's also this fuel called seed oil, which is a type of oil produced by certain plants that you can burn as well for energy. So biofuels are fuels that are produced by living organisms. And the nice thing about biofuels is that they are renewable, because these organisms can, even if they die, we can regrow them very, very quickly. They can produce fuel very quickly, and we don't have to wait millions of years like we do for fossil fuels, and we can get some of those valuable liquid fuels out that way. There's still a question of efficiency with these. Most living organisms they're not designed to provide fuel for us. They're designed to keep themselves alive. So the efficiency of converting the energy input, which is usually solar energy, into the fuel is still very low. So there's a lot of waste that goes into this process as well. But it is another approach that we could think about for the future, and especially things like alcohols. They're already being produced by living organisms and being used as at least fuel additives at the moment. All right, so that's just some random information that the book covers in Chapter 7. Since I had a little bit of extra time today, I wanted to go into some of that, but I encourage you to read those sections on your own, and you'll see on the homework and the test, we're not going to ask you really detailed questions about this stuff, but hopefully you can help relate it to what we've learned in Chapter 7 and see how some of those topics are important for everyday issues related to energy and fuels and transportation and things like that. All right, but the next thing we need to talk about, which is probably the more important point today, was the energetics for ionic bonding. So as I said, your book introduces this in Chapter 3 when they talk about ionic bonding, but at that point we didn't even know what enthalpy was, we didn't know how to balance chemical reactions, we didn't know what Hess's law was. All these different things are important for understanding this, so we're going to cover it now at the more appropriate time. So if we think about the formation of an ionic compound, so remember that let's say KCl is an example, consists of K plus and Cl minus. We want to ask ourselves, what are the energy changes that are involved in taking two elements and combining them to form an ionic compound? We already have some idea of how this works. We said that the metal loses an electron and the nonmetal gains that electron to form positive and negative anions. But why does that even happen? Why is that a spontaneous process? Because usually for processes to happen spontaneously, you need to have a release of energy. So what are the energy changes associated with forming ionic compounds? That's what we're going to try to understand today. So on a very simple level, we can think of the two processes that have to occur in order to form an ionic compound. Ionization is the first one. So remember that for each of these, we're going to either lose or gain an electron. So if we have a gas phase potassium atom, and we lose an electron from that, we learned back in chapter 3 that this process is called ionization, and the energy change or the enthalpy change associated with that is the ionization energy. So reviewing ionization energy, it's the energy change associated with losing an electron, and for potassium, it's 419 kilojoules per mole. All right, so that means if 1 mole of potassium loses an electron, that requires an input of 419 kilojoules. Then the other step is the chlorine is gaining an electron. So that's what we call the electron affinity of chlorine. So the energy change for gaining an electron is called electron affinity. That should be reviewed. And that's minus 349 kilojoules per mole. As we learned last time, we have this thing called Hess's law, which means we can combine two chemical reactions, and then the enthalpy change for the combined reaction is just the sum of the two enthalpy changes for the individual reaction. So if we add these two reactions together, the electron is an intermediate. It's formed as a product in this reaction, and it's a reactant in this reaction. So when we add these together, what we get is the gas phase atoms, potassium and chlorine, reacting with each other to make the two gas phase ions, K plus and Cl minus. So the enthalpy change for this reaction is just the ionization energy of potassium plus the electron affinity for chlorine. We've combined these two reactions. We add the enthalpy changes to get the overall delta H, and that comes out to plus 70 kilojoules. All right, so what that means is that just forming the gas phase ions is unfavorable. But something else that we we'll talk about more in detail in Chapter 9 is that ionic compounds don't just consist of gas phase ions. We know that ionic compounds typically exist as solids, and we'll see more details about that later. So if it's not just these two energies that we have to consider. If we really want to understand the formation of ionic compound and what's the energy change associated with that, we have to consider other terms as well. Okay? So let's look at other steps that can be involved in this. So once we form those two gas phase ions, there's going to be a force of attraction between them. We know that opposite charges attract to each other. So this ion attraction is just an electrostatic interaction of opposite charges, and there's going to be an energy exchange associated with that interaction. And when those ions interact electrostatically, which means the positive and the negative ions attract to each other, that's going to release energy. All right, so an important concept that we'll see in this section is that anytime you have an attractive interaction that it's going to have a delta E or delta H of less than 0, negative isothermic enthalpy change. Let's call them all delta H to be consistent. Okay, so delta H is less than 0 whenever two oppositely charged ions interact with each other. It's hard to measure this exactly, but if we take those two gas phase ions, K plus and Cl minus, and then in the gas phase we combine them to make just one sort of gas phase molecule of KCl, the enthalpy change for this is a little bit hard to measure, but it can be estimated to be about minus 500 kilojoules. So it's a pretty big enthalpy change just by bringing together two oppositely charged ions. But then the more important one for us to consider is what happens when those ions interact with each other in the solid phase, because ionic compounds exist as solids. Again, that's a topic we'll revisit in Chapter 9, but if we take it as a fact that ionic compounds are actually solids, what's the energy of interaction between two ions when they combine from the gas phase to make a solid ionic compound? So instead we take this K plus as a gas phase ion and the Cl minus and make solid KCl. And the difference here is that in the solid phase, instead of, remember that for ionic compounds we don't have discrete KCl molecules, we have repeating units of positive and negative charges. So we have basically alternating positive and negative charges in all dimensions. I'm only going to draw 2 dimensions here because that's the most dimensions I can draw on a piece of paper. But we have alternating positive and negative charges that extend in all directions. So we're forming a lot of interactions, not just interacting 1 K plus and 1 Cl minus, but we have interactions that persist in all 3 directions over many distances. And so the energy change, the enthalpy change associated with this process here, the process of combining 2 gas phase ions to form a solid, is what we call the lattice energy. And that's what we're going to learn about today, is how to calculate the lattice energy for an ionic compound. So this enthalpy change is abbreviated as the lattice enthalpy or the lattice energy. They're both interchangeable. That's going to be some number less than 0, some exothermic process. And what we're going to learn today is how do we determine this value. Alright, so I'll give you fair warning that what we're going to learn today are probably some of the most difficult problem types we'll see in this course because there's a lot going on. We should understand all the individual steps, but we have to put a lot of things together to be able to calculate delta H. And what we're really going to do here in this process is we're going to use just a gigantic application of Hess's law to determine lattice enthalpy. So we learned about Hess's law last time, which is the idea that we can combine energy changes from multiple chemical reactions, add them together, and that gives us an unknown enthalpy change for a new reaction. We're going to do the same thing here to calculate lattice enthalpy, but we're going to use a lot of steps. It's going to be probably 6 or 7 steps in most cases. So let's go through how we do that. So the way we do that is what's called a Born-Haber cycle. So this is going to be the series of steps, and it's going to begin and end with an ionic solid. So both the part that we start with and in the very first step and where we end up in the very last step are ionic solids. So because we're starting and ending at the same species, there's really no enthalpy change for the whole process. So we have a bunch of individual steps that are occurring, and when we add up their enthalpy changes, that has to be equal to 0 because we're starting and ending at the same place. Okay? And so like I said, this is just an application of Hess's law that allows us to find the lattice enthalpy. And don't be confused by this. Lattice energy and lattice enthalpy are going to be used interchangeably in homework assignments and tests. So they mean the exact same thing. All right, so we're going to use Hess's law to help us find what those values are. And the way we arrange a Born-Haber cycle to make it easy to visualize is that we're going to, as I said, do a series of steps that start and end at an ionic compound. Some of those steps are going to have a positive delta H. We're going to put all of those on one side. So we have a bunch of endothermic steps that we're going to consider. And then if we have a bunch of endothermic steps, because the sum has to equal 0, there also has to be exothermic steps on the other side. So the steps that have a negative delta H, the exothermic steps, are going to be arranged on the other side. And because we're starting and ending at the same place, when we add all of them up, they have to equal 0. Positive delta H is endothermic, negative delta H is exothermic. So we're going to have both types of steps involved, and the sum of all those, again, has to be equal to 0. That's the key concept here. So we're going to use, we've talked about some of the steps that we're going to use. We talked about ionization energies, electron affinities. Those are going to be involved in this cycle. But then what we also have are some other steps that we have to consider besides those. So one of them is the formation enthalpy. We talked about formation enthalpy very recently too. So remember that formation enthalpy is a compound forming from the elements. So the first step in a Born-Haber cycle is going to be breaking up the compound into its elements. Remember that formation enthalpy is defined as the elements forming 1 mole of the compound. So for KCl, that would be this step here. And the value for this particular compound, which you wouldn't memorize, but we'd give it to you if you need it, is minus 437. That's for 1 mole of KCl. So that's the enthalpy formation of 1 mole of KCl. We're going to use that as our first step, as we'll see in a second. The other steps that we need are what's called atomization and sublimation. This is something new for us, but as we talked about, a lot of the energy values that we're defining for this, a lot of the enthalpy changes are for gas phase atoms. So in this formation equation, we have potassium as a solid. We need potassium as a solid to go into the gas phase. So that's called sublimation. Well, again, phase changes is something else we'll see in more detail later, but the enthalpy change associated with taking a solid phase metal and moving it into the gas phase, which is part of the process that we need here, is called sublimation. It'll be sometimes abbreviated as delta H of sublimation, little sub, and that means, and the value for this one is plus 89 kilojoules. This is one of our endothermic steps. And then finally, the bond dissociation energy we need in many cases as well, which is breaking covalent bonds. Because as we talked about earlier, when chlorine gains an electron, the electron affinity for chlorine is also defined for a gas phase atom. But in this formation equation, we know that we're using the standard form, which is Cl2. So for this, we'll also need the bond dissociation energy of Cl2 to make 2 chlorine atoms. And remember, we learned about this in Chapter 3 as well. This is called bond energy or delta H of dissociation. Those are both interchangeable, and for chlorine it's going to be plus 244 kilojoules. Alright, so all of the steps that I've mentioned, these 3 steps plus the ionization energy plus the electron affinity, we're going to combine all of those in sequence to form our Born-Haber cycle. So let's see how that works here. So like I said, the most common application of Born-Haber cycles is going to be to find the lattice energy for an ionic compound. So as we talked about, lattice energy is defined as gas phase ions, so K plus and Cl minus, combining to form the ionic solid KCl. So we're going to go around this cycle. We're going to fill in a bunch of individual steps that have known enthalpy changes, and this is going to be our only unknown. We're going to start here at the ionic solid. We're going to move our way around, end up at the gas phase ions, and then the last step is associated with the lattice energy, and we're going to solve for that as our unknown, setting the sum of all these individual steps equal to 0. Alright, so we're going to have to sort of just internalize and learn how this works. As I said, it's a pretty involved process. So we start with our ionic solid, and the first endothermic step in the Born-Haber cycle, all of the endothermic steps which go up in energy are shown on the left here. So the first endothermic step is going to be breaking up the ionic solid KCl into the elements that make it up. So the standard states of the elements for potassium and chlorine, as I said, are potassium plus Cl2. So we're going to break up KCl into potassium and Cl2. And the energy associated with this step is the negative of the delta H of formation. Alright, so remember that delta H of formation is the enthalpy change associated with combining these 2 elements to make KCl. If we're going to do the opposite process, which is taking KCl and breaking it up into elements, then the energy change or enthalpy change for that is the negative of the delta H of formation. So I gave you delta H of formation is minus 437, so the negative of that is plus 437. So this first step here has an enthalpy change of 437 kilojoules. The next thing we're going to do is we have to have two more steps that are involved with taking our solid metal potassium and converting it into K+, which is one of the last species we need before computing lattice enthalpy. So the first thing we do is we take the solid metal and we take it into the gas phase. So at each of these steps here, we're just changing one thing. So in this step here, we're taking potassium as a solid and making it into potassium as a gas. Remember, as we just introduced, this is called the enthalpy of sublimation, and the value that I gave you for this is 89 kilojoules. So the second endothermic step involves an enthalpy change of 89 kilojoules. That takes us up to here. And then the last step to go from potassium gas phase into potassium gas phase ions is to lose an electron from here. Okay, so we lose an electron from potassium to make K+. You haven't done anything to the chlorine yet, so we're still at 1/2 Cl2, and then we have an electron. So that change where we're removing an electron from potassium is called the ionization energy, remember. So this is the ionization energy of potassium, and it has a value of 419 kilojoules. So we've gone up another 419. All right, so all of these energies will be given to you, and we're just trying to solve for this one, which is the unknown. And then the last endothermic step is we need to dissociate the Cl2 into chlorine atoms. So we have 1/2 Cl2 here. We want to end up as Cl-. So that's going to be a two-step process where the first thing we're going to do is we're going to break the chlorine-chlorine bond. So when we do this, we end up with K+. We have one chlorine because we started with 1/2 Cl2. So if we break 1/2 Cl2, we end up with one chlorine atom. And we still have our electron we haven't done anything with. And this step here is the bond dissociation enthalpy of Cl2. But look at this coefficient. We only have 1/2 Cl2. So the enthalpy change associated with breaking 1/2 of a Cl2 is going to be 1/2 times the delta H of dissociation. So if you have coefficients in your individual steps here, you have to make sure you account for those and multiply those accordingly. That's the only time we'll see it here. And so 1/2 times the dissociation enthalpy is 122. I gave that to you earlier as 244. 1/2 of that is 122. And so that gets us up to here. And then the last step before our ions is we're going to add the electron to chlorine. So this electron is going to be added to the chlorine to form K+ and Cl-. Remember that adding an electron to an element is electron affinity. So this step here, which is exothermic, is the electron affinity of chlorine, and it comes in at minus 349 kilojoules. All these are in kilojoules and not in units. So then our only unknown here is the lattice energy, delta H. And so like I said, we're going to set them all equal to 0. So the sum has to equal 0, and that's going to be equal to all of these numbers added together because we're starting here and ending at the same place. So 437 plus 89 plus 419 plus 122 minus 349 plus the lattice enthalpy, set those all equal to 0. So we just have a simple linear equation with one unknown, and so our lattice enthalpy we solve for, and that's going to be minus 718 kilojoules. So one clue when you're doing these problems is that if you get a positive value for the lattice enthalpy, you're wrong. I'll be blunt about that. So this should always be a negative number, which it is here. So that's the first check to see if your answer is reasonable. And like I said, it's just an application of Hess's law. We're doing one step at a time. We're adding up all those steps. The overall delta H is 0 because we're starting and ending at the same place. And we set them all equal to 0. We solve for the unknown. In some cases, one of these other terms could be unknown. Here, the more typical example is solving for the lattice enthalpy. But really, any one of these steps could be your unknown, and if it gave you the lattice enthalpy as a given information, you would just solve for the other one that's not known. So like I said, it's a long, involved process. It's not something you're likely to learn today, but with some practice, hopefully it won't be too bad. All right, let's see one more. I'll just go through this one because I realize it's kind of foolish for me to expect you to do this on your own after one example. But let's look at this one here. Okay, so here we have magnesium bromide. It's important to consider the formula of the ionic compound, MgBr2. And we want to determine the lattice energy of magnesium bromide with all of these steps given. So we have the sublimation of magnesium. Magnesium, remember, is a 2+ cation, so we're going to have the ionization from all the way to 2+. Really, this value here is the sum of the first two ionization energies, which would require losing 2 electrons. We have the vaporization of bromine to bromine gas, because remember the standard state for bromine is a liquid. And we have to also consider the gas phase species. We have dissociation of Br2. We have the electron affinity of bromine. And we have the formation of magnesium bromide. Okay, so we have all those different steps. Let's try to piece them together into a Born-Haber cycle. All right, so let's see what we're going to do here. There's going to be one extra step here we didn't have last time, but we'll see where that is. Okay, so we're starting at the ionic solid, MgBr2. We're trying to determine lattice enthalpy, remember, which is the combination of the ions to form the compound. So the the ions that make up magnesium bromide are magnesium 2 plus and 2 Br minuses. So the lattice enthalpy for this one is going to be defined as taking a gas phase magnesium 2 plus cation, combining it with 2 Br minuses to make MgBr2. We're looking for this value here, the lattice enthalpy. So what's the energy or enthalpy change associated with this step here? So like I said, we're going to start here. We're going to work our way around in a series of steps to produce these 2 ions, and then it's going to leave that as our only unknown. So it's helpful to do these always in the same order, I think, just to get the hang of it. So the first step, like I said, is always going to be dissociating or breaking up the ionic compound into its neutral elements. All right, so this first step here, we're going to go and take this magnesium bromide and make magnesium metal and Br2. Okay? So it's going to be MgBr2. And it breaks up into magnesium and bromine. And those are the standard state elements. So that's the negative of the delta H of formation. If we go to the given information, the delta H of formation for this compound is minus 524. So that means the negative of that is plus 524. So it's 524 kilojoules to break that up into its elements. The next 2 steps are going to involve the metal. So we're always, really for the metal, we're always going to do the same series of steps. Once we break it up into the elements, we're going to sublime the metal to make gas phase metal atoms, and then we're going to ionize the metal. So those 2 steps will be the same for every lattice energy problem. So the next thing we're going to do is break this up, not break it up, we're going to sublime it to make gas phase magnesium. So we're taking the solid magnesium, converting it into gas phase magnesium. That's the enthalpy of sublimation. Sublimation of magnesium solid has an enthalpy change of plus 148. So that's going to be the number we put there. I'm not going to draw this to scale, but then the next step is going to be, as I said, ionization of the metal. So magnesium gets converted to magnesium 2 plus. We'll typically write this as one step. That releases 2 electrons also from the metal. And so in the given information, we're told that the ionization of magnesium 2 all the way to magnesium 2 plus has an enthalpy change of 2187, a very large number. So this is going to be the sum of the first 2 ionization energies, which are given as a combined value of 2187. All right, because it's 2 ionization energies, but they're combined already. And then finally, we have to do some things to the non-metal to break it up into atomic species. So right now it's at Br2. And so the first thing we have to do is vaporize this. So Br2 is a liquid, but the dissociation energy for Br2 is given for us for gas phase bromine. So most of these energy values are associated with gas phase species. So the first thing we have to do is get everything into the gas phase. So if we do that for bromine, we're just changing liquid bromine into gaseous bromine. That's the energy we'll learn more about also in chapter 9, I think it is, but that's called the vaporization enthalpy. And that's given to us as plus 31 kilojoules on the previous slide. And then the last step for the nonmetal is to dissociate it into atoms. So we're going to take our Br2 and we're going to break it up into 2 bromine atoms. Mg2 plus stays the same. Now we have 2 bromine atoms and still 2 electrons. And this one, as we call it, remember, is the enthalpy of dissociation. It's the bond energy for Br2. In this case, we have 1 Br2 because of the stoichiometry of our compound, has two bromines in it, so it's going to be Br2, so we don't have to modify the dissociation enthalpy. This is the dissociation of 1 mole of Br2 is given, and that number from the table is going to be plus 193. So that's our last endothermic step. And then finally, the last thing we have is the two bromines combining with the two electrons to make 2 Br minus. And remember that adding an electron to an L atom is called electron affinity. And this is going to be 2 times the electron affinity for bromine, because we have 2 bromine atoms combining with 2 electrons to make 2 Br minuses. So we have to double the electron affinity, because electron affinity only applies to 1 mole of the substance. And so that's going to be 2 times that number up here, which is minus 331. So a total of minus 662 for that step. There's 2 bromines going to 2 Br minuses. Okay, so those are all the steps and all the known information that we have, and now we just have to add all of them up and set it equal to 0. So 0 is going to be 524 plus 148 plus 2187 plus 31 plus 193 minus 662 plus the lattice enthalpy. And again, we just have to solve for the lattice enthalpy. That's going to be minus 2421 kilojoules. So much larger than the last one, but again, it should be a negative number, which it is. Okay? So that's how we determine lattice enthalpy. You'll see homework problems like this, so I encourage you to do multiple attempts on the homework just to get practice with this. Later on, I will show you, probably in a review session, because I won't have time to go over it in class, there is a somewhat general equation that you can write for lattice enthalpy that depends on all these other steps here. So I can show you that later on, which might be helpful, but I still think understanding the cycle is really the best way to go about these. The last thing we want to talk about with lattice energy is what are the factors that influence the value of lattice energy. So we use those Born-Haber cycles now to calculate 2 different lattice enthalpies, and we saw that they were very different from each other. One was minus 700, one was over minus 2,000, or whatever it was for the last one. Yeah, minus 2,400. So they can vary a lot in terms of their values. So what are the factors that control those values? So there is an equation for lattice enthalpy that we're not going to use, but it helps us to understand what's going on here. So the lattice energy is some constant, which is ill-defined, times Q1, Q2 over R. So if any of you have taken physics courses, this is basically the equation for the energy of interaction between 2 charges. So Q1 and Q2 are the charges of the ions that are in the ionic compound. So Q1 and Q2 are the charges. And then R is the distance between them, which is determined by the ionic radii. So if you have small ions, they're going to be really close together and have a small distance separating them. If you have large ions, they're going to have a larger distance separating them, just like you saw for bond distances earlier. And then the charges are going to be usually +1 or +2, whatever the charge of the ion is, and -1 and -2, whatever the charge of the negative ion is. So if you have larger ions, that corresponds to a smaller lattice enthalpy because the ions are farther apart. Remember that a smaller lattice enthalpy means that it's less negative. So the lattice enthalpy will always be a negative number because it refers to the interaction of 2 opposite charges. So when we say a larger lattice enthalpy, we mean the absolute value of that, or the magnitude of that, is going to be larger. And then if you have higher charges, that's going to correspond to a larger lattice enthalpy. Which, again, larger means more negative. And you can see that from the examples above. MgBr2 and KCl. KCl is +1, -1 cations and anions, and it had a much smaller lattice enthalpy than MgBr2, which has a +2 cation. So the higher the charges in the compound, the higher the lattice enthalpy tends to be. So the other type of problem you'll have to do related to lattice enthalpy is compare them to each other. So here's an example of that, with the lesson we'll cover today. Determine which of the following ionic compounds has the largest lattice energy. So we have a bunch of choices here. When you're doing problems like this, the first thing you want to look at is charge. Only worry about the size of the ions if you have two that have the same charge. Okay? As I said in the last slide, the two factors that influence this are the charge of the ions and then the size of the ions, which governs how close they are to each other. You want to look at charge first, because if you go from a +1, -1 compound, where the product of Q1 and Q2 is -1, and you go to a +2, -2 compound, where the product of the two charges is -4, that's already a factor of 4 difference, and you're never going to have that large of a difference in the radii. Okay, so the radius is a more subtle effect typically on these than the charges. So you want to look at the charges first, and if you're looking for the largest lattice energy like we are here, find the ones that have the highest charges first, and then we'll worry about the sizes if we have to compare those later. So sodium fluoride is +1, -1, so is lithium fluoride, and then the rest of these are all +2 cations paired with -2 anions. So we can automatically eliminate choices A and B, because one of these that has the higher charge is going to have the higher lattice enthalpy. Okay, so now we have to figure out which one of those it is. So if we compare magnesium oxide to magnesium sulfide, remember O2 minus is going to be smaller than S2 minus, because oxygen is above sulfur on the periodic table. Oxygen is smaller than sulfur, so that means magnesium and oxygen are closer together. They're going to have a higher lattice energy. So that one's going to be bigger than those, so we can cross out magnesium sulfide, because that's MgO is bigger. And then if we compare magnesium oxide to beryllium oxide, again, these ones only differ with respect to one ion. Beryllium is smaller than magnesium. It's up higher on the periodic table. So its valence electrons are closer to the nucleus. So beryllium 2+ is smaller than magnesium 2+, which means that this one is going to have a stronger interaction and it's going to have a larger lattice energy. So the one that wins at the end is beryllium oxide. All right, so that's the other type of problem we'll see. We'll look at charge first and then start comparing the size of the ions. All right, we'll start Chapter 8 next time.